Honors Chemistry, and welcome to 8.7, the last section from Chapter 8, where we introduce a new conversion factor, right? Where that's what heat of reaction really is. And at this point, we should be at a place where we recognize every time something relates to pieces of information, that's all it is a conversion factor, right? So when we say heat of reaction, it is the amount of thermal energy that is exchanged between a system and a surrounding during the course of a process, right? So most often we're talking about chemical reactions, but it can be any process, right? So even during like a phase change, for example, or dissolving of a substance in water, right? These are other places that would have a heat of reaction, though we might call it heat of phase change, right? Or heat of solution, but it's the same principle, right? Where it's an amount of energy exchanged, right? And it's per mole reaction, right? So if we take a look here, right, so exothermic means it comes out of the system into the surroundings. Endothermic means that it goes into the system from the surroundings. For chemistry purposes, the system is always the chemical reaction, and the surroundings is whatever medium the chemical reaction happens to be taking place in, right? A lot of them are aqueous, right? So for example, we talked about in the previous unit, precipitation reactions, right? Or acid-base reactions. These are things that often happen with water in the background, right? So in that case, water is the surroundings. The chemical reaction that's happening, right, is the system, right? And the water either absorbs or gives heat. Yes, does that make sense? Okay, so again, convention states that we write it this way, where heat of reaction is equal to sign and then some number of often kilojoules, right? The understood here is that it is per mole reaction. Some books will write it that way and some books don't, right? What that means is this is the amount of energy tied to that chemical reaction and only that one. So we could say that 802.3 kilojoules of heat are released for every 1 mole of methane combusted. We could just as well say that 802.3 kilojoules of heat are released when 2 moles of water are produced. Yes, does that make sense? So we could just use it based on the chemical reaction using whatever the coefficient is, right? Do note that we have talked about heat previously, right? So we talked about Q equals MC delta T back in chapter 3, right? Go flip back there if you need a refresher. And we talked about this as being heat, right? And measured in units of joules primarily, right? But any kind of joules is fine. And it's the heat, right? The amount of thermal energy exchanged. But note that this heat is tied to a mass, right? And that mass is if that mass changes, then the amount of heat changes, yes? Hopefully we can discern from here, right, that these two have a direct relationship, meaning that if my mass goes up, then my heat goes up, yes, right? As in Q will change based on the amount of substance, right? Here, when we talk about the heat of reaction, right, this is tied to a number of moles, meaning that it's already sort of been standardized, right? Q, not a conversion factor, yes? Not a conversion factor, because it is only one piece of information, heat in joules, right? Heat of reaction, conversion factor, because it is an amount of thermal energy per something else, yes? Okay, all right. Let's do a little bit of practice. So these are the skill builders. It says ammonia reacts with oxygen according to this reaction or this equation. Calculate the heat associated with the complete reaction of, so they're saying all of this 155 grams of ammonia react. We can assume, right? So again, we're layering on things, right, from the previous sections where we only know the amount of ammonia. So what that means is we can assume that there is ample oxygen present to make this reaction go, right? And we would like to know the heat. So what's going to get us from ammonia to heat? That's right, the heat of reaction, right? So this is negative 906 kilojoules, and it's per mole reaction. So it's tied to every 4 moles of ammonia, right? Because that's what's from my balanced chemical equation. And that's the conversion factor we're going to have to use, meaning that we've got to turn our 155 grams of ammonia into what? Right. Step one is we've got to get that into moles. And then once we've got it into moles, we can use that conversion factor. Quick and simple two-step problem, molar mass to moles and moles to energy using delta H. Okay, so we'll see that we took our grams, converted it to moles, used our conversion factor to relate energy and ammonia based on our balanced chemical equation. And what we calculate, right, is that for 155 grams of ammonia undergoing this chemical reaction, we would expect the process, the system, to release, right, that's what this negative sign says, right, to release 2.06 times 10 to the third kilojoules of heat to the surroundings, yes? And that's what this balanced equation, this math says. All right, next one. What mass of butane in grams is necessary to produce this much heat, and what mass of CO2 is also produced? Okay, well, so there are two questions here, so let's answer the first one first. Mass of butane in grams, right? And our given is an amount of heat. Oh my, look, we have a conversion factor that relates heat and everything in my balanced equation, right? In this case, we want to relate it to butane, right? Which has a coefficient of 1, right? Which is the mass super easy. So what we're going to do is we're going to start from our kilojoules, and then we're going to do the exact same thing we did here, except it's just backwards, right? So let's get started. So starting with the given of the heat, do note that produce the heat means negative sign. Then we'll use our delta H, which also has a negative sign, and then our molar mass to get our answer. Okay, so what this says is that we would produce, right, or release 1.5 times 10 to the third kilojoules of thermal energy to the surroundings if we combust 33 grams of butane, right? And note the signage here, right? This is an exothermic process, and the question's asking us to produce or release heat, so the signs cancel, right? Note that in the land of partial credit, if you forgot to put this negative sign over here for the produce, then you would get a negative mass, right? Like that's how the math works. So if you decide, well, that doesn't make sense, and you just leave it as positive 33, even though your math doesn't work out, you can't earn the math partial credit points, right? Because you did the math wrong. So these are things that you've got to reason through. If you get a negative mass, go back and figure out why and fix the error, right? Otherwise, you have to leave it as a negative mass with maybe a note saying you understand you've made an error somewhere. But otherwise, you would lose the math partial credit. Okay, next up. What mass of CO2 is produced? So where do we start to get to mass of CO2? Right, we've got a couple of choices here, right? So one, we could just as well start from this again, right? Because we know that that's the amount that we want to produce, or the amount of energy we want to produce. We could also just start from the 33 grams of butane. It doesn't matter. You can pick whichever one you like best, and that's going to get you to the same place. I'm going to choose to start with the negative 1.5 times 10 to the third kilojoules, right? You start with whatever you want, but like I said, either way we'll land in the same place. Similar to the last problem, we will start with our amount of heat that is produced. Then we will use our delta H as tied to the balanced equation. Don't forget that there's a coefficient in this case. And then we'll do our molar mass to get to the mass. So just like the previous step, just with attention to CO2. Okay, and so you'll see here, right, again, we start from our energy, but we use the relationship between the delta H and the CO2, because that's what we're talking about in this case, right, and then the molar mass to get to grams. All right, so that wraps up 8.7 and the practice. Oh, no, it doesn't. We have a concept check. All right, so consider the generic reaction written here. The reaction mixture initially contains 5 moles of A and 6 moles of B. How much heat will have been evolved? What kind of problem is this? Right, we know the amount of A and the amount of B in moles, or we can know the amount in moles, which means that this is a ding, 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 limiting reactant problem, meaning that we have to start from moles of A, right? And we have to start from moles of B to see which is going to limit the amount that we can produce, right? Now here you might be like, okay, well, where do I go to, right? And here that just kind of depends on your comfort level with the problem and the concepts of limiting reactant and stoichiometry, right? If it produces the least amount of product, it's also going to be the one that produces the least amount of energy, yes? So we could just go ahead and relate it to this, right? So this says negative 100 kilojoules, negative 100 kilojoules, right? And that's it. And then we would just see, well, what are we looking for? So here's what our work looks like, right? So which one is the answer? Right, this one is the answer because this is not an amount of energy that can be produced, right? In that once I've produced 200 kilojoules of heat, I will have run out of reactant B because it's the limiting reactant, yes? And so the ideas work the exact same way as they did for the actual discussions of how much product can we make, yes? Okay, now finally, that brings us to a summary of conversion factors to date, right? So now we've learned mole ratios, right? This is the only conversion factor that converts between moles of A, right, and moles of B via a balanced chemical equation. The only one. And that's what makes this one special. Everything else, right, converts within the same thing, right? So if we think about all the conversion factors we learned back in chapter 2, all of those are these, the SI and metric ones, right? So that could be joules to kilojoules, right? Or grams to pounds, right? But it's always of the same thing, right? Like grams of CO2 to pounds of CO2, for example, right? Density, right? That's the same thing. If we want to say grams per mil, right? It's grams of CO2 per 1 milliliter of CO2, right? Temperature, right? In chapter 3, we learn all the basic temperature relationships, right? Between C and Fahrenheit and Kelvin, right? But again, we aren't changing the substance that we're talking about, right? Q equals MC delta T, while it might not feel like a conversion factor, like we talked about before, C really is just a conversion factor, right? When we say joules per grams degrees Celsius, right? That could also be rewritten as joules equal to 1 gram times degrees Celsius, right? And that provides a relationship between the amount of energy and mass and temperature, right? Avogadro's number, right, converts between the number of moles and the number of particles, right, for a given substance, but always for a substance, right? Like 1 mole of CO2 is equal to 6.022 times 10 to the 23rd molecules of CO2, right? Molar mass, right, that's grams and moles of a substance, right? And even percent composition, right, is within a substance still, right? Piece to whole within a substance, right? And so what sets mole ratios apart are that anytime we know we've got to convert between two different chemical compounds, right, or two chemical substances, then that is a clue to you. You need a balanced chemical reaction, and a mole ratio is what has to happen at some point during the problem. All right. Thank you for listening. Be good, and we'll be wrapping up chapter 8 soon. All right. See you soon. Bye.